It's my pleasure to welcome you back. And we have another invited speaker. I'll keep the introduction short, I was told. So yeah, Thomas did a PhD at Paderborn and toured around as a postdoc a little bit, including MPI, and is now in Cambridge. Instead, I wanted to share this little story. He was one of the first people I met when I attended my first conference, which was the SODA 2012 in Kyoto. And I was there because of Analco at the time, which I guess a subset of the people here would have also been. And it was a weird moment because Philippe Flageolet had just passed away, but I never got a chance to meet him. But I got to meet Thomas instead. And well, the comparison now is a bit rough, but we went to this Japanese restaurant where we both had serious trouble scrambling our legs under the table, but the food was great. So I remember this all vividly, but Thomas also does very interesting research, and it's kind of a state of sin that this kind of work has not been as prominent in AofA as it should be, because it's, as you'll see, close in spirit to many things we do. And there should be some cross-fertilization opportunities, to put the fancy words. Well, over to you.
Thank you very much for the colorful and unorthodox introduction. So I'm going to talk about balanced allocation, the power of choice versus noise. And this is joint work with Dimitrios Loss and John Sylvester. Also, as always, feel free to ask any questions throughout and also after the talk. So let me start with some background. So this talk will be all about allocating or throwing balls into bins with some schemes to be defined shortly. And the same abstraction applies to many other settings like hashing or distributed storage systems. And maybe there we would call the same things items into buckets or memory cells. If you're into sports, maybe you would like to throw balls into baskets, or perhaps even more timely would be to throw or kick footballs into goals. But in this talk, I'm going to stick with the balls into bins framework. And this is, I guess, usually used in the context of scheduling or load balancing, where the balls represent jobs or tasks and the bins represent processing units or servers. So a bit more notation. So we want to allocate these balls or tasks into bins or machines. And we will be interested in minimizing the maximum load or the normalized maximum load. So the load will be denoted by X. So X is the load vector across the n bins. I is the index of the bin. And then we're usually interested in the final state when we've allocated all m balls. So therefore, we have this xi to the m. And then the performance of an allocation scheme will be measured by the so-called gap. The gap is just the maximum load minus the average. Okay, so it's a quick example. We have this load configuration, 20 balls into 8 bins. So the average is 2.5, and the gap would be also equal to 2.5. So let's look at some very basic and simple allocation schemes. The first one is one choice. So here, all the m balls are just allocated independently and uniformly at random across the n bins. So this is, I guess, very simple, easy to parallelize, but because there's no coordination. The downside is that the gap, the performance, is not very good. So as soon as m is a little bit larger than n, then we end up with a gap which is growing in m. So we have the square root of m over n, which is just the standard deviation of the load of a bin. And then we also have this extra square root of log n factor. And for those of you who maybe work on probability combinatorics, this is a relatively easy exercise. And the main thing for this talk is just to remember that this grows as m goes to infinity. So we can improve on this greatly if we switch to the so-called, one more thing, this high probability here, I'm using a strong notion, so I have convergence, which is polynomially fast in n. So we can greatly improve on one choice if we switch to the two-choice scheme. So here for every ball, we sample 2 bins, independent uniformly at random, and we allocate the ball into the less loaded of the 2 bins. So here the gap is dramatically smaller, so it can be shown that for any m, the gap is now just log of n plus a constant. And this huge improvement is widely known as power of two choices. Okay, I just want to quickly illustrate the proof idea of this result when m is small. And there's this amazing log or sequence of logs not too far from Bath along the canal, which consists, where the main part consists of 16 blocks. So also 16 is a perfect number for this conference, the power of 2. And this maybe illustrates a bit this idea of induction, or so-called layered induction, which will follow on the next slide. So if m is equal to n, we can use the simpler proof method called layered induction. So let's, as I said, let's say m equals n. And let's denote b of k to be the fraction of bins that have load at least k after all n boards are allocated. So then it's not too hard to prove this approximate probabilistic inequality. So b of k plus 1 is at most bk squared. Okay, and this has to do with the fact that we're taking 2 samples, and in order to increment the load of a bin from k to k plus 1, both of the samples must be a bin that has load at least k. Okay, so this is kind of the induction step, and as a base, we just have deterministically that the fraction of bins that have a load at least 2 is at most a half, thanks to this assumption m equals n, the average load is 1. And then you can just use this inequality. So you're going to repeatedly square this 1/2. So the question is how often you have to square this until you get something polynomially small. And this gives the log n upper bound. So this is not quite a proof, but you can find it in textbooks. But this proof idea completely breaks down if m is much larger than n. And one reason is that already the induction base, this one here, this does no longer work if m is larger than n. And also, we'll have problems with this inequality here. Notice that here we're not really looking into the time. We're only looking at the fractions after all n boards are allocated. And this does no longer work if m is very large. So there's usually a big difference between the m equals n case and when m is much larger than n. Okay, so here's just a quick animation of the two choice. So we all understand how this process works and what kind of load distribution comes out of this. And I should perhaps add that in all these visualizations, the bins are always sorted non-increasingly. So the heavy bins are always on the left and the light bins are on the right. So you can see that the heavier bins have a load quite close to the average. And you can perhaps also see that the light bins may deviate more, but our gap measure is not sensitive. It's only taking into account the heaviest bin. Okay, then here's some experiments. And again, here you see a huge gap between the one choice and the two choice. If you look at the specific numbers here, you will see a gap from 300 to 500 for one choice, and two choice, even if you do 100 repetitions, always ends up with a gap of 2 or 3. Okay, so that means we're getting really small constants, which perhaps also explains why this scheme or these ideas have been proven very useful in practice. And in fact, just 4 years ago, this ACM Theory and Practice Award was given to these 5 pioneers of power of two choices and balanced allocation. Interestingly, so the award was given 2020, but most of the fundamental theory works are 20 or even 25 years old. And as you can see in the citation, they mentioned that these ideas have really been implemented in industry and in very applied real-world settings. Okay, so now I want to talk a bit about variations and relaxations of this original model. And I've just explicitly written out the assumptions or the setting that we were considering before. So the balls are arriving sequentially, one after the other. For every ball, we are taking 2 uniform and independent samples. Then from these samples, we're getting the exact correct load information, and then the balls are located or placed in the less loaded of the 2. So in the following, I'm trying to break this down so I get different directions along which I can relax this model a little bit. So the first one is in the 2-choice setting, we're always taking 2 samples. So what is happening if we are not able to always sample 2 bins? And this gives rise to a process called 1.5 or 1 plus beta choice. The next one is we are sampling independently and uniformly at random. There might be scenarios where there's some kind of geometry or network underlying the bins. This is called balanced allocation on graphs. So the bins form actually vertices of a graph. And then for every ball, we are sampling an edge uniformly at random. And then the ball would be placed in the less loaded endpoint of this edge. The next direction or dimension concerns the load information. So in the original setting, we always assume we get exactly the correct load. So one possibility to weaken is that we assume we cannot get the exact load information. But for every fluid bin, we get to know, is the load above the mean load or is it below? So we have this more binary blurred vision of the bins, as you can see here. So we only know whether the load is above or below this line. This gives rise to a process called thinning, which I'll look at in the second part of this talk. And an even stronger set of models would be where perhaps the load information is outdated. So we have some balls that have maybe not been acknowledged or processed by the bins. And the strongest possible model would be to have perhaps an adversary who's able to both delete and introduce fake balls and making us believe completely wrong load informations of the bins. And if I have time, I will talk about this type of model at the very end of the talk. Okay, so I now want to start by talking a bit more about this 1.5 choice. So the question is, what is happening if we're interpolating between 1 and 2 choice? Just very quickly, if we go higher and we go from 2 to 3 choice, then we only get a relatively modest improvement. So all what changes here is that this first 2 here in this log would become a 3 or a D if we considering the general D choice. So what happens in between? There's this process 1 plus beta. And for the sake of simplicity, I'm going to stick to this 1.5 choice process, where with probably half we're using 1 choice, otherwise we're using 2 choice. Again, this 1/2 could be replaced by any other constant. In fact, also people have looked at cases where this beta is either very close to 0, very close to 1. But let's just stick to the 1.5 choice. So for this process, of course, the number of samples is 1.5 on average. You can also see this 1.5 choice as running 2 choice where you're occasionally making wrong load comparison. So with probably 1/4, the load comparison is incorrect. And it was shown already almost 10 years ago that the gap is still bounded in terms of m. It's not log-log, but it's still log of m. So the gap is still reasonably small. If we run experiments, so here I've added the 1.5 choice, you're getting something like a gap of 9 to 10. Okay, again, it's a flat line here because the x-axis here is growing in m, in the number of balls. Okay, in the following, I want to outline the key machinery which is involved in the proof of this log n gap bound. Yes, sorry, there's a question. Yes. No, actually, if m is equal to n, you would get log over log log with 1 choice, and with 1 I guess with 1.5 choice, you would also get log n over log log. Yeah, sorry, this was probably meant to refer to the case where m is much larger than n. Any other questions? No? Okay. So then I want to talk a little bit about the proof method to establish that the gap is logarithmic. And the first tool are probability vectors. So probability vectors nicely encode the way we are allocating balls. So P sub I will be the probability that we're allocating to the ith heaviest ball in step T. So, and 1 choice, 2 choice, also 1.5 choice will be allocation scheme where this P of T is the same for all steps T. So it's a time invariant allocation. So for 1 choice, it's just uniform. It's oblivious to the load configuration. But if we have 2 choice, then we have some strong bias. So what's the probability that we allocate into the heaviest bin? Well, we need to sample that bin exactly twice. So we get 1 over n squared. So this is a massive bias away from placing a ball into the heaviest bin. If we look at the probability for allocating to the lightest bin, where we have this roughly 2 over n minus a low order term because we are sampling with replacement. So roughly 2 over n probability is that we increment the lightest bin. So we get this green line as a probability vector. And now for 1.5 choice, of course, we just take the average of these probability allocation vectors. So we still have a reasonably skewed allocation vector. Yes, so in conclusion, first, what is very nice here is that we have time invariant probability vectors. So this is, of course, great simplification for the analysis. We see that both for 2 choice, more, but also for 1.5 choice, we have a bias towards the light bins and away from the heavier bins. And while looking at the probability vectors also seems, of course, the more choices you have, the better the result should be. This is generally true, but for some noise models, this is actually not true, which is why I've added the question mark. Okay, so that is the first tool. The next tool is a potential function. This has been called exponential potential or hyperbolic potential function. So this again depends on the time t, and we have 2 sums. We have an overload potential and underload potential. So the overload potential, we are penalizing deviations of the heavier bins. Yeah, so we have e to the alpha. Alpha is some parameter, and then we have the load of bin I minus the average load. And for the underload potential, it's the same. We just have a minus alpha here. Okay, so if you plot this, we've got this red and the green functions. We add them up, and then we get this hyperbolic shape. And now if we apply this to a load configuration like this, let's first write out the normalized load vector, which is this. And then just for each of these numbers, we stick it into this potential function, and then we add up the contributions. And you see that for bin number 5, which has the largest deviation, this bin also contributes the most to this potential. So we get 126. And the way we are going to use this potential method is that we will establish that with high probability, this gamma t, this hyperbolic potential, is polynomial in n. And then because it's an exponential function, I can directly deduce that the gap is logarithmic in n. Okay, so that is the plan. Now, how do I prove that the exponential potential is always polynomial? I'll just do a step-by-step, a round-by-round analysis. So here's again the definition. Now I'm going to choose this beautiful constant, 1 over 144. So I think that's the largest one for which this works, or at least or perhaps the most convenient. I don't recall, to be honest. But at least this constant works. And we look at the change in 1 round. So we prove a drop inequality, the expectation of this potential in round t plus 1 conditional on the previous step. And here's was just one example of a load profile. So again, we have sorted the bins decreasingly in their load. And here's again the tool number 1, the probability vector. And now we can just relatively crudely divide the bins into groups. So the first, let's say, a third or fourth of the bins are highly overloaded. But for all of those, we have a small probability, much smaller than uniform probability to increment the load here. So that means the contribution of these bins to the potential will go down. For the ones in the middle, where they have a relatively small contribution to the potential, so we can just assume maybe their contribution will slightly increase. We can be generous. And then for the last bit, we've got this heavily underloaded bins. They have a larger than uniform probability to increase the load, which also means the contribution of these bins to the potential, or more specific to the underload potential, will overall result in a net decrease of this potential. So I end up with this multiplicative drop of order 1 minus theta 1 over n. So this is maybe morally or conceptually true, but mathematically, of course, it's not true, because that would mean the potential would always go down, but it could be 0. So to make it correct, I have to add just another constant C2. But once you have established this, of course, I didn't go through all cases. So you'd maybe have 3 or 4 more cases of this type. But in all of these cases, you would get this drop inequality. And once you have this drop inequality, you directly get the unconditional expectation bound. So at any step, the expected value of this potential is linear in n. And then you can just use Markov's inequality to prove that with high probability, the potential is, let's say, order n squared. And then you get that the gap is log n. Okay, so this works, I think, quite nicely. And now I want to move to another process for which the analysis is actually more involved and more interesting. And this process is called mean thinning. So this process, this allocation process works as follows. So for every ball, every time step, we are sampling 2 bins, I1 and I2. Again, the samples are uniform independently. And if the first sample, I1, has a load less than the average, then we're allocating the ball directly at I1. So we're not going to check even the second sample. So here's an example. We're sampling a bin whose load is below the average, and then the ball will be directly allocated to that sample. The other case, if the load of the bin is equal or greater than the average load, then we're allocating the ball into the second sample, but again, without inspecting the second sample. So this is different from both 1.5 and 2 choice. And in the second case, where we might be lucky or unlucky, so this first case, which is illustrated here, okay, we sampled I1. I1 is above the average. We take another sample and directly allocate the ball there. So here we are lucky, right? So our second sample has less load than I1. But there's also possibility that we have bad luck and we place the ball into a heavier bin. Okay, so is this process clear? Not, feel free to ask questions, slow me down. So yeah, let me first show you, again, a small visualization, and then I state the main results. Perhaps I can speed this up a little bit. There's always a question what you can deduce from these small examples. Hopefully you can at least understand the process better. And it seems, yeah. Ah, yes. I guess then you would, yeah, this would be another process. It would obviously, would be seemingly better. But okay, I mean, the gap bound would be still the same. So I'm not sure whether we analyze this explicitly, but the gap would be also logarithmic in n. And maybe for some practical applications, it's actually nice that you only need to query the load of 1 bin. So actually, I think I will explain this a bit more on the next slide. Okay, but yeah, first, the main results. So we can prove that for any number of balls, the gap of this mean thinning is logarithmic. And also one can prove that this is tight. So there's a matching lower bound if M is large enough. And the analysis of the upper bound also has an interesting corollary or consequence, which is that in a constant fraction of the steps, we are allocating to the first sample. So that means on average, we are requiring less than 2 samples. And this is maybe a bit related to this question. We can also implement mean thinning in this way. So we don't take immediately 2 samples. We first just sample 1 bin. We check the load and we allocate the ball to that bin if the load is below the average. And otherwise, we sample the second bin and allocate it there. So what it means is that when the ball queries the first bin and the first bin has a load below the average, maybe that, has a load above the average, then this first bin can also directly allocate or relocate the ball to another bin. So you don't need to go back to the user. So it avoids also this requirement of sampling 2 bins, waiting for the response, and then only then you decide which bin to go to. So I'm not an expert in practical applications, but it seems that maybe for some distributed applications, this is a maybe more communication efficient and more sampling efficient allocation scheme. Okay. So now I want to talk a bit about the analysis, and perhaps most of the time will be spent to explaining why the analysis is difficult rather than how the analysis is done. So the challenge here is that the probability vector now depends on T, or more precisely, it will depend on the proportion of overloaded and underloaded bin. So to this end, let me introduce this delta T. This is the mean quantile. So this is a fraction of bins that have load at least the average. And then there might be load configuration where this delta T is either very close to 0 or very close to 1. For example, if it's as large as possible, so it could be 1 minus 1 over n, which means that all but 1 bin is overloaded. And in this case, the process performs or behaves very, very close to one choice, which you can also see from this probability vector. So the first n minus 1 entries are all very close to 1 over n. And then the final one is, okay, this is a bit different, of course, from 1 over n. But in terms of most of the probability measures and the actual behavior, it will be too close to one choice. So if the process always uses this probability vector, then we are doomed. We are screwed. And here's again an illustration of such a configuration. So you can see all but 1 bin is slightly overloaded, and you have 1 massively underloaded bin. So the question is, how can we prove a drop in the exponential potential function? And it took us actually a long time to solve this problem. Maybe as an analogy, we were like looking into this dark, long tunnel. There's some lights. Actually, this tunnel here is a tunnel in the south of Bath, where you can even cycle or walk through. And it's also promising not only the lights, but also the fact that the length is 1.6 kilometers. So it's 16 to the power of 2. So maybe this gives us some encouragement that we can still do the analysis with some tweaks. So let's take a closer look at this exponential potential function. Again, if you find this, if you choose this scaling parameter alpha suitably, we can look into 2 cases. So let's first assume we're in a good case or good step. So this quantile delta T is neither too close to 0 nor too close to 1. Now we are in a setting which is very close to the 1.5 choice, and we can prove an analogous drop inequality. So that's the easy case or the good case. The bad case is, of course, if this quantile is not balanced. For example, like this. When in this case the process is close to 1 choice, But this means I can at least upper bound the increase. So now I have this factor here, which is slightly larger than 1. And what's maybe also nice here is that I get an alpha squared, which intuitively comes from the fact that this is an unbiased process. Okay, and now if I want to combine these good and bad steps, then of course now I need to prove somehow that the process is most of the time in a good step. So how can we prove that there at least a constant fraction of the good steps? So I will outline this on the next slide. And the answer to this, or at least our approach, involves the introduction of 2 more potential functions. So again, this is our goal. We want to prove that there's a healthy fraction of overloaded and underloaded bins. And the next potential function we're going to use is the so-called absolute value potential function. So this is some kind of linear function, which also has the absolute values. And again, if I draw just the load profile like this delta t is just the blue area. Okay. So if I now make one more perhaps seemingly optimistic assumption, if this delta t was linear, then I would be kind of close to a good step. And why is that? Well, most of the bins would have a load which is not too far away from the average. This just follows by some first moment computation. So I have this green area here where bins are either just slightly overloaded or slightly underloaded. And now just exploiting that the probabilities of this process are close to 1 over n, you can prove that if you have a bin which is overloaded, then the probability that we allocate to it is less than 1 over n. So there's a chance we never choose this bin for n balls or so, and then the average load increases, which means that this overloaded bin has a constant probability of becoming underloaded if you just wait for linear number of additional balls. And similar for an underloaded bin, the probability that we allocate to it in one step is larger than 1 over n. So there's a decent chance that this bin catches up and becomes overloaded. So we have these bins that are like oscillating between overloaded and underloaded. And combining this with some slightly tedious but straightforward probabilistic arguments, you can prove that if you wait for these many steps, you will have a healthy mix of overloaded and underloaded bins. And this nice equilibrium will also remain for a linear number of rounds. So that means we are now basically done. The only catch is that I haven't explained how to prove that this delta t, this linear or this absolute value potential is linear in most steps. And here I will just add one more bullet point, which is that if you now look at the third potential function, the quadratic potential, and you look at the change in one round, then you get this minus delta t plus the linear term in n. Okay, and since the quadratic potential cannot become negative, this delta t cannot be dominant here. This cannot be always a large constant times n. So using this interplay between the quadratic potential and delta t, one can deduce that for most steps, delta t is bounded by a large constant times n. Okay, I want to stop with the mean thinning here. Are there any questions? Yeah.
This is also the same. This is basically the same as 2 because you just put it in the overload bin unless you're set unless you choose the underload. Why is it difficult for me? But not difficult.
But I mean, for 2 choice, you would have a 2 over n probability. Oh, sorry. Yes, okay, that's a good point. But the problem is for 2 choice, you wouldn't have this one choice type allocation on the left bins, on the overloaded bins. And actually, I think that maybe on the next slide, yeah, I think maybe this may also, well, I'm not sure it directly answers, but it's related to your question. Yeah. So I will now actually show just as the last slide on this, there's some experiments that in a way, well, it's always hard to argue that you have to use a particular proof, but maybe give some evidence that this process may stabilize or recover more slowly. So if you start with this load configuration, this has around 200 balls. And I'm plotting here these three potential functions, exponential, quadratic, and absolute. Then you see that these low order potentials, quadratic and linear, they go down relatively smoothly. But the exponential potential function, due to the fact that we have this one single heavily underloaded bin, which means that this quanta is not stabilized. So we are doing some kind of one-choice process over these bins for quite a substantial time, which means that there's a decent chance that you have this high fluctuations. And even after throwing another 200 balls, the exponential may increase dramatically. And only after these 250 balls, you can see that we have recovered now reasonably well. So here you can see we've got more bins whose load is close to the average, and you can also see that here the exponential potential function seems to be going down. Okay, so I guess it doesn't really prove that you need to use all this family or this zoo of potential functions, but maybe it gives some clue that you have to do some at least some smarter analysis. You can't just directly use the exponential potential function without some other tricks. Okay, I have a few more minutes. Now I want to move on to a different part, which will be less technical. Oh, sorry. Yeah, maybe I'll skip this part. There are a few more results about this thinning, but I want to go to a different model, the noisy comparisons. So now we're going to run the two-choice process, but the load estimates will be noisy or faulty. So the framework is as follows. Again, we've got P denoting the ball index. Now every ball takes 2 samples. And for the 2 sampled bins, we're getting not necessarily the correct loads, we're getting load estimates. Therefore, I'm using this tilde here, xi and xj, and we're always allocating the ball to the more promising load estimates. So this is not yet a process, this is just a general framework. Now the load estimates, they could be adversarial perturbations, meaning the load estimates must be within some specified parameter g, within the must be within g of the true load xi. This again, one example here where g is equal to 4, so this adversary can remove and add balls as long as the load does not change by more than g of a single bin. We could have some random perturbations where each load is perturbed by a standard Gaussian, or we could also have delayed load information. So the load estimate can be any load values which is up to capital T many steps in the past. I want to focus on the adversarial model because this is in a way the strongest, and also in terms of the proof techniques. Once we understand this, we can relatively easily get results for the other two. So first I want to slightly change this framework. So this was based on load estimates. You can also just slightly reformulate it, rephrase it in terms of comparisons. So we're now going to assume that the adversary can directly control the outcome of load comparisons. And so one specific process, this name was not, it's not by us, this was in previous work called G-bounded process. So G is the parameter. Again, we're doing two choice, and whenever the load difference is less than G or equal to G, then the adversary can fool us and present the heavier bin as the lighter bin, and vice versa. If the load difference is larger than G, then we are allocating into the lighter bin. Okay, so in a way, you could say that the adversary is, well, greedily fooling us as often as possible. The question is, what kind of gap do we obtain for this process? So there's a sketch here of the asymptotic results. So first, if G is larger than log n, there it's relatively easy to prove this bound of G plus log n, again using the exponential potential method. And things get more interesting if this parameter G is less than log n. And well, of course, if G is equal to 0, then we are back to the original model. We are always doing correct comparisons. So we have the log n here. And now, annoyingly, even if we just increase G a little bit from 0 to 1, we were not able to do any coupling or reduction, which maybe at first sight seems plausible, but we were not able to not even get an O of log n here. So we had to do a proof by hand. But it is theta of log. And then maybe the general question is, how does this gap here behave between a constant and log n? It turns out the answer is this slightly concave function log n times G over log G. So to prove this, you have to use stronger than exponential potential functions, of course, because we're having sublogarithmic gaps. So the analysis is more complicated. And finally, I want to mention that for all values of G, we're having also matching lower bounds. And these lower bounds are already tied even if the load comparison is correct with probability half. So you don't necessarily need the adversary fooling us in all steps. It suffices if it's a 50-50. Okay, I think I should maybe jump to the conclusions now. So in this talk, I presented several tight bounds for noisy versions of the two-choice process and relaxations. So the proof techniques, these are the ones we used, were always based on combining several potential functions. For thinning, we used the exponential potential function in conjunction with a linear and quadratic potential function. And for these noisy versions of two-choice, as soon as we want the sublogarithmic gap bounds, we also have to use super exponential potential functions. I maybe didn't emphasize this earlier, but of course, we were always assuming that the balls are like the same size, unit size jobs or tasks, and also the bins are completely heterogeneous and not distinguishable. Some of the results can be extended also to weighted balls, to allocations on graphs, and also we have some results where the bins are not homogeneous. In terms of open problem, so I spent a lot of time talking about mean thinning, where the threshold is the average load. What is very interesting is that if you do experiments, it seems that if you slightly increase this threshold, so you accept the bin if the load is the average plus, say, square root of log n, then you can reduce the gap from log to log over log. So you get an improvement in terms of the gap. But also, secondly, if you are more tolerant, so if your threshold is the average plus square root of log, and you're also accepting more balls directly to the first sample, so you're also becoming much more sampling efficient. So this is one major open problem we're trying to solve, proving this improvement of the gap to log n over log n using different thresholds. Unfortunately, this seems very hard. So if there's someone in the audience who likes to work on this or has some ideas in terms of techniques, please talk to me. For balanced allocation, as I hinted at before, we also have some results, but they're mostly for very dense expander graphs with polynomial degree. And understanding this process on sparse graphs like cycles and grids is still very much open. And maybe even more open-ended question is, what are more other realistic noise models? And with this, I want to finish the talk. And this is nice final animation by my student. So thank you very much. I'm looking forward to your questions.
The wrong question to ask. Other questions for Thomas?
So did I understand this correctly that all the asymptotic results are in the number of balls that you put in and not depend so that the number of bins is fixed in that perspective? Meaning you at the very beginning you had one choice versus two choice, meaning that there was, what was it, square root of m divided by n, and it was, so the asymptotics is in m.
No, I mean, we're always thinking of both m and n being large. Maybe m, yeah, I mean, m and n going to infinity, but also m growing much larger than n. So I guess it's like a multivariate.
Okay, so then you had one choice that was decreasing in n and two choice increasing in m, right? Yeah. Is there one?
So you mean,
Yeah,
oops, sorry.
exactly. Yeah. So the first formula says it's decreasing in the number n, and the second is increasing in the number n. Can that say it be that way, or is it because the asymptotics is somewhat different?
I mean, for this result, I guess you need m being at least n times log n. So m is always larger than n, or actually even should be even larger than n log n.
Okay.
And I guess, well, this result, I mean, I guess trivially, it also holds for m being between 1 and n. But,
Okay.
maybe if you have fewer balls than bins, that's also not so interesting.
Okay.
Yeah.
I have to think about it. Thank you.
I think one of the point was that the bound was decreasing it.
Oh, I see.
Yeah. So is that really how you can see it, or is that just because the asymptotics is more?
Yeah, but I guess if you fix m and you're increasing n, you're also moving to a slightly weird scenario, right? Where you have many more bins than balls. So, and you need, and also your n is bounded by m, right? I mean, m should be larger than n log n. So I guess you can't really fix m and then increase n arbitrarily. I mean, if you check this reference, I think there are 3 or 4 different, there's like a table or like a case, 4 different cases or regimes for m and n, and for each regime, they have lower and upper bounds. So maybe the best would be to check this reference rather than only trusting my slides. But I think if m is larger than n log n, this should hold.
More questions? Close.
So could you explain what it means to do balance allocation on graphs? So would that case correspond to the complete graph or?
Yes, yes.
Okay.
And some of the results that we proved, but this is more like a side effect, they would also apply to very dense expanders or dense random graphs where the degree is a polynomial in n. So these are very clique-like graphs with constant diameter. So we got some results basically for free for this restricted class of graphs, but for, yeah, even for G and P, where P is log n over n, or even more basic graphs like cycles or grids, we don't have tight bounds for the gap. So it seems you need to use much different or more sophisticated tools. Because I guess all the ideas I presented here, they're only working because we have a complete graph in a way. Yeah. Yeah, I mean, there's a...
That you take the first from the first half and the second from the second half.
Yeah, I think there's a scheme, a so-called asymmetric load balancing scheme by Ferking, the last author, who I think managed to slightly improve over this gap bound.
But that would be like.
But it uses some kind of partitioning.
That would be a complete tripartite or tripartite graph, right? Because you allow every edge.
Yes. I guess it would be some kind of hypergraph, right? Not a graph.
At least
No, with 2. Sorry, with 2. Yeah. You're right. It's a good point. I think when this was done in 2000, and maybe at this I don't think anyone had looked at graphic allocations on graphs. So this is like a nice perspective. But it's again a dense graph, right? So I think sparse graphs are just much harder.
Are there things known about when things go badly wrong? So one of these low probability events happens and the gap is much bigger than normal. What it looks like. So some kind of large deviations result and some kind of idea of what. So you can think of various things. It could be just like two bins continually get paired together and there's nothing the system can do other than allow it to get large, or it could be 3 or 4 or many bins that get overloaded together. Are those kind of bad events understood?
I mean, we have this high probability results on the gap, right? Usually they're coming from some expected bounds on some potential function. So you would also get some bounds on the number of bins exceeding a certain load.
And so then conditioned on the gap.
Yeah.
N to the alpha or something instead of log n. Can you say what?
I think in that paper, they also explicitly study, they call this like recovery time. And so I think they have some bounds on how long it takes until a certain gap is reduced. I also guess our results should prove something. I mean, I guess it should be linear. Let's say if you have one single bin with.
I wasn't so much asking about the recovery time, but more just like what's an unlikely bad configuration actually looks like.
What an unlikely. Oh, well, I mean, I had one, right? One in these for thinning. Oops, where is it? This one here. I can't recall the exact, but we also have a mathematical result, I think, which gives some theoretical results more or less matching, well, not exactly matching, but in line with these experiments.
So that one is definitely bad, but it could also be that one has very, very unlikely.
Ah, yes.
Events which are more likely. But yeah, anyway.
But may I take your point that probably a lot of our analysis is a bit obsessed and fixated on the gap, and maybe there are other interesting things we could look at. So yeah, maybe we can discuss.
Even when the gap is large.
Yeah, okay.
Other questions?
Yeah. Is there any work somewhere on the dynamic version? That means N and M are large, fixed. In one step, you delete a random element and then you add a random element. You delete one, you add one. And the dynamics of that process.
There are queuing ones.
Yeah.
So there are models where your queues are servers.
Yeah.
And you also have a writers.
Yeah. That's sort of. So what are the gaps then?
I think in this already first work by Azar et al., I think they also have one process of that, but yeah.
Oh.
Mm. And so you would do two choice on both, right? Then when you allocate, you do two choice, and when you remove.
Well, you can do that with where the service has one choice and the errors are two. And what you get is like station distribution, but instead of like exponential terms, you have double exponential.
Yes, and the reference is 96. Dobroshin, Vedenskaya, Karpelevich.
This one? So did you say 26?
96.
90, 96?
Yes.
Ah, sorry, the year. Oh, no,
Yes. Yes, yes.
Yes.
sorry, what 96 there? Because there's no slide 96. You mean the year 96?
No, yeah.
Oh, sorry. So yeah, which reference?
Dobroshin Vedenskaya Karpelevich.
So which
It's the non-reference for the queuing model.
Oh, I see. Okay, yeah, if you could
And-
send this to me.
My question is, can you say more about your experiment to find a better threshold?
To find a
At-
better, oh, yes, okay. Actually, I had
It-
one slide, I skipped it for,
And my question
one.
is the threshold adaptive or?
so
Of
for this
fixed.
experiment, it would be, well, the threshold is, oh, sorry, this is bar now. It's, for mean thinning, the threshold is just T over N. So of course it has to be like depending on time. Oh, sorry, how do I get rid of the bar? And on the left, you see some experiments where this Fn ranges between -10 and 10. And so you get some unimodal shape. And, oops. Yeah, it's maybe a bit difficult to see, and also not sure what you can conclude from the experiments, but it seems you get a slightly smaller gap if your threshold is a bit more generous, a bit above the average. And there are also results by, this is Feldheim, Grigorovich, and Lee, who prove for some more tailored strategy, if you're given the round M as an input, that you can achieve an almost square root of log n gap. And you can achieve also this gap for most of the rounds. So like 1 minus little o of 1. So there's much more known also for general strategies.
More questions? Okay. Thanks a lot.
Okay. Thank you.
Thomas.